All right, so can we all see the presentation?
Yep.
All right, very good. So I will be talking a bit today about my research involving small-scale topography and the temperature distribution of the permanently shadowed regions on the moon. So if you have seen the show For All Mankind, then you will know that in the year 1979, NASA established Jamestown Base, the first long-term human settlement on a planet outside of the Earth. Now, of course, For All Mankind is a work of fiction, but there is, real-world science behind the showrunner's decision to locate the base here at the rim of Shackleton Crater. You see, Shackleton Crater contains one of the many permanently shadowed regions, or PSRs, present at both of the moon's poles. PSRs are a consequence of the fact that the moon's rotational axis is inclined just about 1.5 degrees relative to the plane of the ecliptic. This means that near the poles, the sun is always either just above or just below the zero elevation horizon. If the local horizon is more than a few degrees above zero in all directions, as it is at the center of craters, then the sun will never rise. PSRs are of scientific interest because in the absence of direct sunlight, they can reach temperatures low enough for volatile materials like water to remain stable over geologically long timescales. These volatiles could theoretically be extracted and processed for use in a lunar base, thereby avoiding or, at least ameliorating the need for regular resupply missions from Earth. So because the stability of lunar volatiles is so strongly dependent on surface temperatures, temperature maps are among the best tools we have for determining how much of the moon's surface is available for the cold trapping of various volatile species. The best data we currently have are from the Diviner Lunar Radiometer experiment on board the Lunar Reconnaissance Orbiter. These data indicate that while most PSRs are able to efficiently trap water, there are not many areas that reach temperatures low enough to trap other species like methane, ammonia, and carbon dioxide. However, the Diviner data have one serious limitation: their resolution. At 240 meters per pixel, these data are good for examining large-scale patterns in temperature distributions, but they also average over a lot of fine details at smaller scales. Just take a look at this elevation map of York and the surrounding area, taken at a resolution of 0.5 meter per pixel. If we downsample it to match the lunar data, it's obvious that a lot of information is lost. Now, you might be wondering why the resolution actually matters. There has been recent work suggesting that so-called micro cold traps on scales down to a centimeter might greatly expand the moon's cold trapping area outside of PSRs by up to 10 to 20%. However, this work specifically focused on otherwise sunlit terrain where small areas of permanent shadow would be averaged over by the Diviner data. This differs from PSRs, which by definition cannot get any more shadowed than they already are. Or can they? Though PSRs are protected from direct sunlight, they aren't completely dark. They're subject to a number of alternate sources of illumination, the most significant of which is sunlight that has been scattered off of nearby illuminated terrain. Though faint, this light is substantial enough that it has been used to image the interior of PSRs in the search for surface exposed ice. It is not unreasonable to assume then that small-scale terrain features within PSRs may create areas that are shielded from both direct and scattered sunlight. Without either of the primary illumination sources, these areas could be much colder than the rest of the PSR, perhaps even cold enough to harbor volatiles other than water. This is the question that my research aims to answer. To what extent does the small-scale structure of the lunar surface affect the temperature distribution of the permanently shadowed regions? So this question can be answered in, as I see it, approximately 3 steps. First, increasing the resolution of existing terrain models with artificial rough terrain. Second, I will need to model the direct and singly scattered sunlight incident upon the terrain. And finally, I will need to convert these instant solar fluxes into temperatures. Now, this first step is, in my opinion, both conceptually and procedurally the easiest of the 3. So first, I have to take the original terrain maps, which is seen here on the left, and I will need to upscale them through interpolation. This is sort of, this figure shows the progress of my various interpolation methods, ending up here on the right with the final version. Now, this interpolated higher resolution terrain is still unrealistically smooth. It's no roughness at all. It's very much unlike how the lunar surface actually is. So on top of this interpolated terrain, we need to add this artificial rough terrain, which we then need to fine tune the parameters of this terrain so that its characteristics match those that have been measured for the actual lunar surface. And so once this is layered on top of the interpolated terrain maps, you have this high resolution, artificial terrain map that is, more or less consistent with what one might expect to see, actually on the moon. All right, so to find scattered light, we basically have to answer two questions. Which terrain elements have a direct line of sight to the PSR? And which terrain elements are illuminated, and how much light do they scatter into the PSR? Now, while conceptually easy, these questions are, surprisingly computationally expensive to answer, largely just because of the sheer number of calculations required, that you have to run for every terrain point, both in the scattering terrain and in the PSR terrain. This becomes exponentially more significant as we move into higher resolution data. So in an attempt to mitigate some of this expense, I've been leaning very heavily on some of the work done by another member of our group, Jake Kloos, who recently published a paper on looking at all these various alternate illumination sources. So to answer this first question, I've been using these scattering terrain maps like the one seen on this slide, which essentially indicate which terrain elements outside of the PSR are able to scatter light to at least one portion of the PSR. And then for each of the scattering terrain points, there's an associated local horizon map, which basically gives the the elevation angle of the horizon in 1 degree increments of azimuth. So then by comparing the location of the sun, the elevation of the sun at the appropriate azimuth, I can determine which scattering terrain elements are illuminated at a particular time. Then to determine how much light is being scattered into the PSR, I'm assuming that the moon is a Lambertian scatterer, which basically just means that the amount of light being scattered off the terrain is only a function of the incident angle. This is a simplification, as the moon has been demonstrated to not actually be a perfect Lambertian scatterer, but it is not an entirely unreasonable simplification. So then finally, we come to thermal modeling. This is, in my opinion, the most complicated part of this whole procedure because it requires carefully looking at how the lunar regolith responds to light that's incident upon it. And so for that reason, it is still under heavy development, still to come in the future. So not much work has been done to date, but will be coming in the future. So to summarize everything, PSRs are likely to play an important role in the future of lunar exploration, thanks to their ability to trap volatile materials like water that could be used to support future crewed bases. However, despite their importance, our knowledge of potential volatile distributions is currently constrained by low resolution data. As a consequence, more detailed studies either from orbit or on the ground are likely needed in advance of the site selection for the Artemis Base Camp, which is theorized to take place by the end of this decade. Bit of exciting news on that front about a month or so ago when the Canadian Space Agency announced that Canada would be sending a rover to the south polar region of the moon, perhaps to study some of this. So that brings us to the end of my presentation, and I will take any questions that you might have.
So I had one. So you had shown some generation of some like local topology by fitting using these two fit parameters like sigma and h, I believe. Do you expect those fit parameters to be a function of a location around the planet? Or sorry, yeah, the moon.
Yeah, I mean, we do know that the characteristics of the lunar surface do depend strongly on location. For example, the two general groups that we see is basically the lunar Maria versus the lunar highlands. They have very different characteristics from each other. But within each of those categories, the terrain is roughly consistent from place to place.
Okay. Interesting. Does anyone else have any more questions?